All right, so in this video 1.2, we're going to talk about multiplicative grouping systems. Simple grouping systems led to multiplicative grouping systems where two sets of symbols were employed multiplicatively. There was still no zero. All right. Examples of multiplicative grouping systems would be traditional Chinese and Mari. Right. So in traditional Chinese about 1500 BC. As with simple grouping systems discussed earlier, this system also used base 10, and there is that familiarity. So the idea that if we're working with base 10 across the different, I'll call it languages, there is that common root where as long as we can understand base 10, and that's something that we use typically, that everything kind of relates in a meaningful way, or I would say a recognizable way. But then also throw in there that eventually we're going to be moving over to different bases, so that's going to introduce its own set of challenges. Right? These symbols were then used in conjunction with symbols for powers of 10 as placeholder symbols. Numerals were written vertically, right? So just to kind of give you a little refresher, it's basically like saying if I have the number 325, we've been thinking of that as 3 times 100 plus 2 times 10 plus 5. And then we would use appropriate symbolism to replace out the 100 or the 10 and so on, right? But I could also think of this as 3 times 10 to the second plus 2 times 10 to the first plus 5 times 10 to the 0th power, right? Each one of them representing, we call it a place or a placeholder, but essentially they're all powers of 10, right? So that's the idea. And if I know that 10 is this T looking symbol, 100, which would be 10 to the second power, is this symbol, then we would also have, I only use 325 as an example, but we could have something in the thousands, the 10,000, and so on. This could be 10 to the third power, or this is 10 to the third power, I should say. 10 to the fourth power, and then we can go on and on and on from there. All right. So the different symbols represent the result after raising 10 to a particular power. And we also have the numbers 1 through 9, the symbols that correspond with those. A little bit more challenging to draw out than the case of Roman numerals. Probably on the same level of difficulty in terms of just keeping track of the strokes as probably the Egyptian, right? So, there are some characters that we use for simplicity, right? So instead of this very intricate looking symbol, we could use something a little bit less complicated, right? So the number 4, so looking at the bottom here, the number 4 would just simply be this symbol for 4. All right. But 40 we would look at as the product of 4 and 10 to the first power. Right. So all of these, when I was saying 10 to the 0th power, those would all correspond to anything to the 0th power. 10 to the 0th power is 1. 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3, and so on. Right. But then once we get 10 and above, then we have to incorporate those other powers of 10. All right, so when I look at 40, it's a product of 4 and 10. So I just use the symbol for 4 and the symbol for 10 in conjunction with one another. All right, 400, the symbol of 4, or 4, that's weird to say, and the symbol for 100 in conjunction, organized vertically. So if I were doing 625 in traditional Chinese, I would have the 600, which is broken down into 6 and 100. All right, so we use the symbol for 6. I'll use my highlighter here. All right, And while I'm here, oh, I didn't want to do that. What I will do, like I've been doing before, is I'll just kind of bring the table along for the ride. I'm just going to move this out of the way while I make a copy real quick. All right, apologies for my inability to trace out in a straight line, but the app fortunately recognizes it. So I'll copy, and I'll just kind of move this back into the fray. Oh, undo. Okay, so I'll bring this into the conversation down here, a little tiny version of the graph, but that's good enough. All right, so you could see the symbol for 6 here. All right, the symbol for 10. 10 to the second power. That would be this one. Then corresponds with this. The 2, that's the equal sign looking one. The 10 is the plus sign looking one. All right, so I'm just trying to color code here as reasonably as possible. And then the 5 itself is just standalone character, right? And I would say, I mean, this is an online course, but even if it were an in-person course, there's no real expectation that you would memorize these symbols. You would have a reference table, and we'll get closer and closer to talking about exams and things like that. But as we get closer, I'll talk more about that, and I'll post up on online different resources. But having a reference table with the different characters and what they represent is something that you can expect. All right. So then you see in the next example, the 38,106. All right. So it's the same general idea. All right. So let me bring my diagram down. Do a little duplication, bring it on down. All right. So the one key addition here, because we're learning about these numerical systems in the order in which they occurred in a historical context, right? So what I have, or what we have here in bold, is any missing place values in a number indicated by a 0 as a placeholder in modern day convention were simply left out originally, right? So that's something to bear in mind, all right? So we'll have a look at that, and then we'll address it as we come along. But 38,000 could be thought of as the sum of, just thinking about it the way we've been doing everything else, 30,000 plus 8,000 plus 100 plus 0, 10, like if you think about it that way. So like if we're thinking about this in the most explicit way, instead of saying 30,000, I would say, oops, I don't know why it does that. 3 times 10,000 plus 8 times 1,000 plus 1 times 100. And then it's like, well, where's my 10? Where's my tens place? That's technically 0 times 10 plus 6 times 1. All right, now I'm going to tuck it all in here, but if I write this as 3 times 10 to the 4th power plus 8 times 10 to the 3rd power plus 1 times 10 to the 2nd power plus 0 times 10 to the 1st power plus 6 times 10 to the 0th power, you'll see that every power in the explicit form, where I'm going from left to right and accounting for every single digit, every power of 10 is accounted for, starting with the power of 4 and decreasing down to a power of 0. Right? But in my expansion here, what we would say is, if it doesn't have a digit, like in the case of the 0 here, it doesn't have a digit. Well, it does have a digit. It just happens to be a 0. But in this earlier convention for writing numbers using these characters, they were just simply disregarded. So that's why you would see that there's nothing addressed in my solution corresponding with that 0. We go from 30,000 to 8,000 to 100, and then we skip the tens place and go right down to 6. All right. Then we use our characters for 3. That's the triple horizontal line. All right. So that's this one here. That addresses this. So we're good to go there. At 10,000, we use the simpler version of that character. We do the same thing for the 8. We grab an 8. We grab the character for 1,000, which is the little cross with a little hat on it. Then the character for 100. All right. I just want to make sure I have enough highlighters here. Grab my character for... Oh, I already selected a color for that one. Look at me. All right. The 1. So all of these things just coming right from the table. And then a 6. I don't think I've used this color yet. And again, I'm looking at the string of characters. I've accounted for everything except for a 0 and a 10, because if you look at my number list, going from 1 to 9, then 10 and on, there is no character for 0. All right. Now I could put a tens place in, but it would be basically, if I wanted to be proper about this, I'd have this symbol. And I'd have this one. That's the best I can draw it. Obviously not too skilled with this, but I do my best. All right, I have my... All right, so I have the 30,000. I have the 8,000, so I have 38,000. I have the 100. All right. So then I would have something for 0, which is unknown at this point. All right. And then I would have a 10. And then I would have my 6. All right. And that would be, if we incorporated the concept of 0, that would be the full expansion. But since at this point 0 hadn't been conceptualized, at least in terms of a character, there really wasn't any way to represent it. So you could see how some things could get lost in the shuffle. But as long as you know that you're working with powers of 10 and you know what the symbols are that correspond with those powers of 10, then you can easily fill in the gaps. But it does create a little bit of uncertainty, especially when you're first kind of getting used to this. All right. So the other thing that we can do is go in the opposite direction. All right. So the first thing I would do whenever I tackle these, fortunately the characters, which I think are probably the hardest part, from where I'm sitting, the characters, if I can establish what's what, I know that every other one is going to be a power of 10, right? So this is my 10 to the third. It's going to go from largest to smallest. So 10 to the third. I got my 10 to the second. All right. 10 to the first. So then after that, anything would just be the zeros place. So now I'm just grabbing the numerical equivalents. All right, so I got a 5 here. I got a 6. I got a 2. And I got another 5. All right, so these two together give me 5,000. These two together get me 600. 20, and then the 5. So 5,625. All right. There is an element of this where you're like, well, I'm really just reading it off of a table. Yes, but it's developing mathematical thought, right? The idea is that we're trying to get an idea. Well, the idea is that we're trying to sort of put ourselves in the shoes of the people that were coming up with these numerical systems as they were doing it. All right. So you have to imagine that you're developing fluency with this to the point where you have sight recognition, and you're not just looking at it and comparing it to a table. That would be sort of like translating a sentence into another language word by word. Right. There's some things, if you had to look up even like simple articles, like a and the and things like that, it would take forever. So there's some things that you want to recognize on sight. Now I understand it's pretty challenging, so we're not going to really hold to that. But if you're really trying to interpret this, that's pretty much the approach you would take. All right. Oh, sorry, little typo here. This is one that I've been meaning to fix. This is not correct. By the time you get a hold of this handout or this packet textbook, the edit will already have been made. All right. So that first character there is a 9. This is a 10 to the 4th. You'll notice I'm writing it as powers of 10. For the sake of a couple of things. One, I don't want to have to write so many zeros, especially if I get higher than a power of 10. But also, this is connecting to something that we're going to cover down the line, the idea of bases of numerical systems. All right, so it's just kind of a good habit to get into. All right, 10 to the 2nd, and I have a 2, and then I have 10 to the 1st, so this is a 4 zeros, so 90,600, and then we'd have 20. 90,000 plus 600 plus 20 is 90,620. All right. The short notation, place value symbols were later dropped to simplify notation, unless there was a need to indicate the missing order of a digit. For example, differentiate between 47 and 407. You throw in the symbol for 100. All right, so for the 47, for example, if I wrote that out using all the appropriate characters, I would have this symbol. Oops. Clean that up a little bit. And then I would have this symbol. All right. Let me get the tens place in there. So that would give us a cross. All right. As opposed to the 407, I would need a 4, character for 4, character for 100. All right, so that's this one. Then I would need a character for the 7. All right, so I didn't really leave myself enough room, so let me move this over. Just kind of tuck it in over here. All right, the tens play. Now, if we did know what 0 was at this point, I would tuck that in there, and then I would follow that up with the tens place. All right, which would be that, and then I would have my 7 in there. All right, but if I'm using the shorthand notation, what would happen is I would strip away any indication of a placeholder. All right, so I would take away this power of 10, and I would just have that to represent the 47. Right? I would do the same thing here. This would go. This would go. I didn't have anything for this to begin with, so this is what I'd be left with. So 407 would have the same array of characters as 47, right? So it would lead obviously to some confusion, right? So the way to fix that would be to have the placeholder associated with the 4, right, indicating that that's going to put us out 3 digits instead of 2 digits, right? So I'm going to hang on to this one. I'm going to lose this stuff because it can't be there anyway because we don't know what 0 is and we don't need the placeholder. So what I would have here is 400, because that would be 4 times the 100, and then this one would be the 7, put it together, and you get 407, right? So slight difference in terms of how it's handled, but it gets the job done, and it gets it done without having to incorporate a 0 into the conversation. All right, so I'm just going to throw that down here, and I'll group all this stuff together and toss it. So the idea for short notation on the traditional Chinese, it would just be we have 3 digits. And maybe this is what you would think it would be early on, you know? So you would say, right, if I wanted to write the number 19, I would take the character for 1 and the character for 9. So it's like, what's up with this 10 to the 1 power, 10 to the 2 power, whatever. But the shorthand way of writing it would be kind of like the way we would say it. So if I have 3,792, I might not say it that way. I might just say 3792, right? Everybody knows what we're talking about. So it really is just a matter of kind of everybody being sort of on the same page. And when you are, we all know what we're talking about. So you can have those conversations in a simpler way. All right. So really, that's all we're doing here. If I want 625, I'm just grabbing the character for 6, 2, and 5. All right, and that's all that's really happening. All right, same idea for 5,201, except we do need that placeholder. All right, so here I'm looking at the 5. Easy enough on the 5. I'll use the yellow. Then the 2. But that 2 is occupying the 100s place. So I need that 100 symbol. All right, so that would be this character. I need that 100 symbol to account for that 2, right? And then, I'm sorry, not to count for the 2, to account for the 0, right? So you got to imagine that there is a 0 times 10 here. All right. So we're getting the times 10 part of it in there, but we're leaving off the 0. All right. Just as a placeholder. All right. Going the other way, same idea. It really is. I mean, it's just going to boil down to the ability to recognize what your powers of 10 are. All right. So if I can see characters, and this is from short notation, it's important that it's indicated that it's the short notation. This is my symbol for 3, all right? This is my symbol for 10 to the 3rd power, all right? This is my symbol for 6 and my symbol for 9, all right? So what's happening here is I have that placeholder accounting for the thousands place, all right? So 3 zeros essentially, like the 3rd 0 in. So the 3 is good. Then this is my 10 to the 3rd, 6, and followed by the 9. All right. Same idea for number 8. All right, I got my symbol for 7. All right. Then I have my symbol for 9. And I have an additional placeholder. This is the 10 to the second power. All right. So here we're looking at 900. We got the 7, we got the 900. And there's nothing that follows that, so that would be the end of it. All right. So now if I want to add and subtract, I'm essentially following the digits. As long as I line the digits up appropriately, it's not going to be overly challenging. All right. I do have to bear in mind that there could be placeholders involved, so we have to kind of be careful, but essentially it's not going to be too bad. So the numbers are organized vertically, so we would add them across horizontally and just identify the appropriate symbol. And if we have any carryover, we account for that, right? So if I have, in this case, my character for a 9, there's nothing to pair with it, all right? So I would just leave that alone, at least for now. When I do my sums, for example, I have a 6 and an 8. All right. So 6 and an 8 would get me a 14. So I'm looking at this as the number 14, but 14 is a horizontal slash and this symbol. Right. So what's happening is we're taking the bottom digit of that, and then we carry over to be part of our sum the leftover 1. So then I would take my 5. All right, so this is going to be the same as saying 5 plus 5 plus 7. So it's going to give me a 12, but then I have the additional carryover. So that's going to give me 13. All right, so my symbol for 13, let me change the color here. My symbol for 13 would be a single line and a 3. And just be careful the way you draw it, but that's what we're looking at. So that would get me, this corresponds with this, and I still have a leftover 1. All right, so that's going to go in my carryover column. I'm going to now add a 3 and a 4. All right, 3 and a 4 will give me a 7, plus the 1 in the carryover column is going to get me an 8, and the symbol for 8 is, well, it's this symbol. All right, and so, and again, there's nothing to pair with the 9, so we're left with a 9, an 8, a 3, and a 4. All right, so 9, 8, 3, and 4 would give you 9,834. All right, so the same idea would be true for subtraction, except we would, instead of carrying over, we would be borrowing as needed. But it works the same way that subtraction works for us. It's just obviously we're working with different symbols and we're doing it horizontally instead of vertically.